Now, what this means is the following. Okay, now I think we spent too much time on that. I wasn't planning to spend that much time. Okay, now so now if I write down the first equation, right? So lambda xt is equal to h11 xs plus what was it? h12 ys. No, h11 h1 okay, plus h13, right? Then lambda ys on the left will be h21 xs plus h22 ys plus h23, and then lambda, right? Third will be just lambda is h31 xs plus h32 ys plus h33, right? This is what you have. Now if I want xt, right? So xt I can get as lambda xt by lambda, right? And of course, all of this lambda is assumed right, to be not equal to 0. So lambda xt by lambda, so that is like h11 xs plus h12 ys plus h13 by h31 xs plus h32 ys plus h33. Similarly, I can say I need, if I want my yt, that will be lambda this should be yt, right? Not ys, right? Lambda yt. So lambda yt by lambda, that is h21 xs plus h22 ys plus h23 by again the same lambda, which is h31 xs plus h32 ys plus h33. So now if you simply do a cross multiplication, then what do you get? Then you get like a h31 xt xs plus h32 xt ys plus h33 xt is equal to h11 xs plus h12 ys plus h13, and then for yt, right, you will get h31 xs yt plus h32 yt ys plus h33 yt, it is equal to h21 xs plus h22 ys plus h23. Okay, what this then means is that, see, for example, right, I can actually think about my unknowns as h11. If I stack them as a vector h12, h21, no, h13, h11, h12, h13, h21, h22, h23, h31, h32, h33, right? If this is my vector, then on the left hand side, right, you will get, this is actually 9 cross 1, right? Okay, so you will get actually 2 columns, right? So what this means is that, so the standard way to kind of say represent this is like minus, so yeah, so you bring whatever is on the right hand side, right, here, so it will be like minus xs, right? So that is what is multiplying h11, then minus ys, that is multiplying, I do not know whether I have space to write this, then h13 is minus 1, and then h31, so it is like 0 0 0, right, because you do not have anything for h21s. I mean, I'm just rewriting this one, right, in the form of matrix vector, and then, oh wait a minute, h31, right, so that will be xt xs, xt into xs, okay, by the way, h32 is xt ys and h33 is xt. And similarly for the second coordinate, what will I have? So I will have h11 does not even come in, right, so I will have like 0 0 0. Then I have h21 for which it is minus xs, then minus ys, then minus 1, and then what is it? h31 is xs yt. Okay, I mean this became small, okay, but I hope you are able to follow, right? And then you have got h32 is yt ys, and finally yt. This is okay, right? This is rewriting these two equations in a kind of a matrix vector form, because this is the unknown. This is the homography matrix represented as a 9 cross 1 vector. So now this matrix on the left is actually A, and what you have, what this means is that if you had one point correspondence, right, between the two images, that means, right, what this means is that See, when I say xt, yt, xs, ys, that means that for the source and so suppose I had image I1, then I had image I2, and suppose I wanted to know what is the motion between the two. By motion I mean this homography H, not the camera motion, right. How do I relate the two? Then what it means is given one point here, and then if I know this one point correspondence, I can get actually two equations, correct. Given one point correspondence, I can get say two equations. And right, because of the fact that I have only 8 unknowns in my H. So what this means, if I have 4 point correspondences, okay, this I write for 1 point correspondence, give me one more point correspondence, which you know now to do, use shift or something, get shift or get one more, get a third, get a fourth, okay. Then it means that, right, I have already got, you see, 8 cross 9. If you give me 4 point correspondences, I have got 8 equations there, which then means that I already have something like AH equal to 0. Where this 0 will be what, 8 cross 1, okay, this is 9 cross 1, this is 8 cross 9, okay. Now ideally, right, you should be able to solve this, right, I mean, so and then right, because of the fact that right, A is 8 cross 9, right, so it clearly means that there is one kind of say non-zero H, which actually A should actually map to 0, right, and that kind of and that I mean what do you call that, is non-zero H will be this homography, and it can only be found out to a scale factor, because A lambda H is also equal to lambda H, that will also be equal to 0, right. So, the H you can only find up to a scale factor, which is okay, right, that we know right from the start. So, what this means is that if you had 4 point correspondences coming from whatever you have studied already, if you could just run shift or something between the two images, and if you have this point correspondence, then it means that you can actually, you know, what do you call de-warp, right, in a sense, right. So, you have the other image which is warped version of this. Typically we use warping for more this one more what do you call sort of a difficult case, but let me just say that this is geometrically transformed, and you can apply an inverse transformation, right, so that these two are aligned. Because why do you want them to be aligned? I mean, you might want to stitch them, you might want to find a change, whatever you want to do, unless you align, right, you cannot do, right, any of that. And therefore, this alignment. So, as you can see, right, did we ever bother about what was the camera translation, what is the original camera rotation? We didn't at all have to bother about it. I mean, there could be some people who are interested in all of that. That will mean going back and solving an inverse problem, but we are not here for that, right. We just want to know so that is what I said. So, by the end of this class, you should be able to take your mobile, capture images like this, click, 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 right, take 5, 6 images, whatever you want, and be able to stitch them all together to get a panorama. And that will come provided you are able to run shift. That is part of your next assignment, and then you get the point correspondence, and then you should be. But then we do not stop here actually, right. This is not the way okay, it is actually done. So, what is done is, because of the fact that these point correspondences can be noisy. See, most of the time it is not exact, because you are running a shift, and then it need not be exactly correct, right. So, if you just take these, this would be an exact solution provided those point correspondences are absolutely accurate, then it is okay, then you can do it this way. But there is no guarantee that what you have is going to give you exact point correspondences, because that is coming from say another method, some like shift or something, right, that is going to return, and then there is no guarantee that it is returning exact matches. So, if there are some outliers, right, then there is a problem, because this does not handle outliers. Okay, so, to handle outliers, there is something called what is called a RANSAC, okay, and what this means is random sample consensus, and this has nothing to do with homography and anything. This is something which comes from the CS literature, and it is actually a nice idea. What it says is anytime right, you have a set of points, right, and then you have a model, and you want to find out a best fit to the model. Then what you should do is, and so for example, ideally, right, you should have had a straight line, right, which you had to fit, but then if you have these noisy points, then how best to kind of fit this line, right. And therefore, if you knew what was the model, of course, you have to know what the model is. Then say this RANSAC, what it does is it tries to tell you, it tries to give you a proper sort of a systematic way to actually arrive at this fitting of this model. So, in this case, our model is actually this is a homography. Okay, that is what we want to find, and we know that the minimum number of points that we need to fit a homography is 4. Okay, so we start from there. So, whatever model you fit, you have to look at the minimum number of these point observations, right, that you need in order to be able to fit a model. So, in our case, right, we know that. So, for example, right, imagine that right, I have I have, let us say, right, a set of points for which the feature correspondences are available, right. I could have say m number of them. Earlier we were taking m equal to, okay, well, we have m by 2 feature correspondences, right, and because every correspondence gives you 2 equations, or in other words, if you had m point correspondences, you will have 2m equations, okay, in that matrix. Now, we know that to kind of start with, okay, we said that if you had m equal to 4, we could solve the problem, but now we are saying that we could have outliers, right, which can spoil the entire thing. Therefore, what we will do is, we will start with, so that I will just kind of write down the steps quickly, okay, because shouldn't take long. What happened? Hey, I was writing something. So pick any 4 point correspondences, okay, and solve for h. What would you then do next? So, you know that, right, I mean, if I have 4 point correspondence, I can solve for it. What will you do next? Will you just accept it? You don't want to accept it, right? You want to check how good is this, and to check how good is, you should basically apply it on the other points, right? Because you have so many of them, right? So, you could have picked at random any 4, you can compute the homography, so you solve that AH, we will see how to solve AH equal to 0, right, at the end. You can do SPD or something and get the H vector, which you can just reshape it in the form of a matrix, which is H, and then apply, right. Then what do you do? So, use this H to calculate so you should focus on the fact that there should be a consensus, right. It is like a voting. So, use this H to calculate, let me say xi double dash is equal to, why is okay, I think yeah, okay. So instead of using xt yt, right, so a notation here is like x dash, okay, y dash, okay, that is the reason why this dash is coming. So, it is like saying that in the left image or whatever, in one of the images, the coordinates you are representing it as xy, and then the pair that is the feature correspondence is x dash y dash. Okay, now what you are trying to do is, so it is like this, right. So, what you are trying to do is, you have actually, so you have taken 4 of these, okay, for which the point correspondences are known, okay. So, you have taken these 4, you got the point correspondence, you know the point correspondences, you solve for H. Now, what you are doing is, you are applying it on these others here, and you know that, let us say, right, somebody already told you, see SIF told you, right, that this ought to go here to some dash, okay, this is like, let us say, x phi dash, okay, let us say, right. So, you have got x1, x2, x3, x4, let us say this is x phi, this is x phi to x phi dash, then somebody said this is actually x6 dash and so on, right, x6 going to x6 dash. Now, what we are doing is, by applying h on x phi or x6 or something, we are trying to get to x double dash, because we do not know whether we reach x dash, right, we may not reach x dash, x phi dash, right, we may not reach it. So, which is the reason why we are kind of denoting it as xi double dash, because where the homography takes it, we do not know. Ideally, it should be taking it to xi dash. I mean, if it was a very good homography, it should take you directly, and if the shift was correct, right, both things have to work, right. So use this, so xi double dash is equal to h times xi, what is that, x times xi, where these xi's are those coordinates other than the ones that you have used for computing the homography. These are not the same 4, they will go, because that is how you computed h, right, not on them, okay. For the u is equal to, what is this, and similarly y, and yi double dash is equal to h times yi for the remaining xi's and yi's, for the remaining xi's, yi's, remaining means other than the 4, okay, that you had used for computing h. Then, okay, now you need to see normalize, okay, normalize xi double dash and yi double dash by what? By dividing the first 2 elements. So, it is like this, right. So, you have got xi, so you are calling xi double dash, yi double dash and some lambda, right, which could be sitting here. So, you have like lambda, 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 and this is h applied on xi yi1, Okay, that is how you need to apply. Okay. And once you apply it, then this lambda, right, it may be 1, it may not be 1. So, we will anyway scale these two guys by lambda. So, that we get the actual image coordinates. Want the image coordinates? No. By dividing the divide by the because the third row whatever it yields.
Yeah, because we do not know.
We do not know exactly. If it is 1, then of course you do not have to do anything. By dividing this third element of by dividing the first two elements of hxi by its third element, right. Then what you have to do, we still do not know how good is this. We have to still check right whether we would exactly. So, we have to compute some error now, right. So, what will you find? Root of xi dash minus xi double dash square plus yi dash minus yi double dash square. Should not be xi yi, right, because you are going to the other image where the feature correspondence is xi dash yi dash, right. I mean here, no, you are going here, right. So, you want to compare it with that original whatever SIFT gave. SIFT would have said that this goes to xi dash yi dash. The homography is saying that it goes to xi double dash yi double dash. Ideally, the two should be the same, they may not be the same. Okay, though find this, right, and if this number, okay, let us call this, right, this is equal to epsilon, then if epsilon is less than a threshold, okay, now this is all not in terms of any intensities, these are all in the spatial coordinate now, okay, we are not talking about intensities, we are talking about how close we are. And therefore, if you set a threshold, let us say if you say that anything less than 1 pixel distance, I am okay with it, that is something that, right, you should take a call on. So, once you decide a threshold, right, then you add it to a consensus set, which means that it satisfies, that means this xi yi satisfies my, so this homography is able to push this xi yi in the right manner within a tolerance. So, then update is a consensus. So, then if this happens, then increment this is consensus set, increment the consensus set. This consensus set is for whom? H, yeah, exactly, consensus set for that H that you derived from those 4 point correspondences, right. And now, and if the total number of consensus points, if the total number of consensus points is greater than a threshold again, right. So, these are some hyperparameters that you should have, but these are pretty robust, okay, than a threshold, okay. And so, this is like, I mean, out of those points, whether you want to say that 60% of them, whether they are obeying the consensus, this kind of tolerance, then we can stop, okay. Else continue for a fixed number of iterations until this, else continue for a fixed number. I mean, sometimes, right, if you are not able to, but actually you can show that you can do pretty well. But in case let us say you are still going on and on, you may just want to stop after a fixed number of iterations, but take the one whichever gave you the maximum consensus, not like the last one. Does not mean that wherever you end you take that, right, that need not be a good one. So, you should take the one that whatever worked out the best. Continue for a fixed number of iterations. Is that clear? And choose the H with maximum, yeah, 1 minute, let me just finish this, and choose the H with the maximum consensus. And one more thing is that, right, you don't simply stop. So, what you also additionally do is you don't simply take that H directly, right. So, you know that out of all of these points there are 4 points for which the H seems to be the best. Then what you do is when you solve for this AH equal to 0, you don't directly use that H, okay. I mean, you have already done this AH equal to 0, got some H, no. What you do is you now put all the points which are actually within that set, within the consensus set, and then solve, you resolve. Makes sense, no, because right, I mean, you could, I mean, if you wanted some kind of, some sort of a stability against noise and so on, what will you do? I mean, you will try to use as many observations as you want, but now these are not outliers, these are all inliers, right, because these have all satisfied the tolerance criterion. So, it is like saying that I have got 4 points, but then I find that out of my 100 points, there are 40 more which are actually good, So, why should I just use 4? I will use all the 44. I will use the original 4 plus the other 40, put them all into this A matrix and solve for H again. Okay, that H is going to be, that is the H that I will eventually use, not the one that I got originally just with those 4 points, but I know which H to, so I know where to go to kind of get that as a consensus set. It is saying which point should I choose to get at my model, right? Is that okay? Okay. Now, the only thing right which remains is how do you solve this now? Okay. Now that we know that, okay, now let me also write that step maybe, right, just that so that do I have, okay, and so then resolve, I'll just write this down, resolve for H using all the say inliers. And this RANSAC is something that you can use anywhere. Okay, it's not just on homography. Any problem that you have, in fact, there are some latest additions, updates to RANSAC that can even do with 5% of inliers. You can still fit a model. You can have 95% outliers. Okay, even with just 5% of inliers, you can still fit a good model. Okay, now the point is, right. So now what you have is like AH equal to 0. This is what you solve, and now A is some m cross 9. This is like 9 cross 1, this is now a vector, right, m cross 1, and this m is much larger than 8. Okay. This is like now a least squares kind of thing, right. So now right, you have a lot of observations, and now there is also no guarantee that you can satisfy this now, right, because of noise. So what do? You'll find out, you'll try to right, minimize norm of AH square with respect to H. Right, I mean, you will just find that H which will minimize the norm, because you can no longer expect that right, you will be able to find an H that will actually satisfy AH equal to 0. If it happens, it's good, but then there is no guarantee. There could still be noise, right, in your final shift correspondence. There could still be some noise. This is just inliers, right. It means that within a tolerance level they are all good. That means there is still some scope for noise in there. Therefore, what would we do? So, which means that this is like AH transpose AH, right, which is like H transpose A transpose AH, right, and therefore right, what you want to find is that H which will actually minimize this is a length of AH, right. That is what you want to do, and therefore, one of the standard ways to do it is use what is called SVD, which you all know, singular value decomposition, which is like taking any rectangular matrix for that matter, you can decompose it as U sigma V transpose. So, let us say in this case you have got m cross 9. Therefore, U is actually an orthogonal matrix, m cross m, this will be m cross 9, this will be 9 cross 9, and U transposes identity, V transposes identity, but this will have a different size, of course. This is like m cross m, be like 9 cross 9. Okay, and then once you plug that in here, right, then you will get H transpose A transpose AH. If you actually plug in the singular value decomposition expression for A, then you will get H transpose, then A transpose is V sigma transpose U transpose, then AH, right. So, A is U sigma V transpose. So, U transpose U is identity, right. So, these are all these are actually inverses of each other, and therefore, you get like H transpose sigma V sigma transpose sigma V transpose, and sigma transpose sigma is what? Sigma is m cross 9. So, this is 9 cross 9, right, and what it contains are what are called the singular values of A. Okay, this is something that if you don't know, just going to say read it up. Okay, SPD, if you're not familiar, just read it up. It contains what are called the singular values: sigma 1 square, sigma 2 square, sigma 9 square. What are the singular values actually? What are they? They are the eigenvalues of actually A transpose A. Okay, they are just the they are basically the root of the eigenvalues. Okay, root of the eigenvalues of A transpose A, but square. I mean, I'm indicating these are sigma 1 square, sigma 2 square up to sigma 9 square. That is what this guy will be, and therefore, and you can order them, right. You can order the columns of V such that the singular values are in the order of the top one being sigma 1 square and the smallest one being sigma 9 square. It can so happen that sigma 9 square can also be 0. Okay, it depends upon how your point correspondences are, but that will be the smallest value. Okay, then what do you do? So, for example, if you now take H to be, let us say, V9, okay, that is the last column of V, right. So, if you take H to be you need an H, right. So, if you take H to be V9, right, you can show that that is what will like minimize this norm, because then you have like H transpose, which will then become V9 transpose, and then V, and then you've got like a diagonal matrix here, and then V transpose, and then it's going to multiply V9, and we know that V transpose V is identity. Therefore, this will give you a vector which will have all zeros except for the last entry, which will be 1, because V transpose V is identity, you know, right. So, V9 is but the last column of V. So, V transpose is just that row, right. So, row column, so it will give you, this is okay, right, this is straightforward, right? So, I am not going to try to explain this and all in great detail, because this just follows, and therefore, right, if you multiply a diagonal with this, what will you get? You will get another vector which will be 0 0, that sigma 9 square at the end, if you multiply this with this vector, and yeah, exactly. And now, so now V into this is what? So, 0 into the first column of V plus 0 into the second column of V plus sigma 9 square into the last column of V. The last column of V is V9. Therefore, you will get V9 transpose sigma 9 square V9, but then this is just a scalar, right, and V9 transpose V9 is 1, because V transpose V is 1. Therefore, you get sigma 9 square, and we have ordered this whole thing such that sigma 9 square is actually the smallest singular value, right. And therefore, if you pick if you do singular value decomposition of A, whatever be the size, and then if you take the vector, the last column of V, that is your H, and then you can reshape it now, right, because I really want it to be a homography matrix. Therefore, you can reshape it. So, the H that you got, you write it back in that form, H11, H12, H is like H11, it is a vector, right. So, write it back in the form of a matrix. You want to ask something? Well, see, for example, right, because H can be found out only up to a scalar. In this case, it is saying H transpose H is 1, the norm is 1, that is the constraint. V transpose V, no, that is the constraint, because it can be only found up to, but you can use any constraint, but going by SPD will actually mean that you are putting a constraint that norm of H is 1. And then the idea is that say once you have this H, right. So, what this means is, if you wanted to stitch a panorama now, what would you do? Right. So, for example, okay, we are almost done now. So, I have, let's say, right, let's say 5 images, okay, which you have captured with your camera. Take the one which is at the center, okay, so that the motion is is not too much on either side. If you take the first one, then this motion is going to be too large, right, with the fifth one. So, you take the middle one, and then you should actually create a canvas, which is on which right, you want to create this effect, and then this central image, right, is going to be here. And now what you do is, now with respect to all of this, right, you have your H21 whatever, right, you have your H21, you have your H31, you have your whatever, right, I mean, if you want to call this H41, then you have your H51, you have all these matrices, all these homographies which you can find now. You know how to find the homographies given the point correspondences. You have all of this. Now, all that it means is, go from this canvas, right, I mean, apply each one and then see where it goes, right. I mean, sometimes what can happen is, there could be an overlap. That means, a point here could map here inside as well as it could map here inside. That means, it is appearing in both the views, right, in which case you can take simply a median of those values. It could come in multiple views, no, because some overlap can also happen. It is not like there is no overlap. If there is an overlap, then you will see that applying the inverse homography will actually take you to the same scene point in, let's say, right, multiple images. You can either take the average of those values, or you can take the median of those values and then plant them here. You continue doing this, then you can actually fill up the whole canvas, and that is how you get this wide picture that you have, right, that you see in your phone. Okay. And you saw that nowhere did we need to know to answer you, right. We never needed to know what was the camera motion. We don't need to know. We don't want to know. Okay.